Lydia, you see, we say this is carbon. Why does it have 4 sticks attached to it?
The sticks are used to describe the valence electrons, and since we have carbon has valence electrons 4, and the valence electrons are the electrons that are found in the outermost shell, so it's used to describe the valence electrons.
Okay, as a follow-up, this is blue, it represents nitrogen. How many valence electrons does nitrogen have?
5.
So then why don't we see 5 sticks?
These ones are
we will have some demonstration using models. Why do we use models? Why can't we use the substances as they are? Instead of taking a model for carbon dioxide, can't we take carbon dioxide? This room is rich in carbon dioxide. Why do we use models?
Perhaps
Yes?
it's because it's hard to obtain carbon dioxide from the air.
Some of the substances we need are invisible, maybe.
Yeah, we can't see them with our naked eyes. Even with the help of a microscope, they're not visible. When do we use models? Okay, when it is really tiny, you represent it with something that's big enough to be seen. Do we use smaller models for huge objects that we may not be able to bring into the room?
Yes.
An example? It doesn't have to be chemistry. Any example? Assume this is, yes?
For example, in physics, we cannot have the exact pulley that we use outside, so we use a model pulley that is smaller to demonstrate it.
Yes, I agree with you, but this has limitations. If you want to teach early grade students, you don't talk about pulleys in them, but we talk about planets, the moon. Would you please bring the moon into the room so that can we do that? It's too big to fit into our room. Even if you are capable to drag it, I doubt if you can do that. So models are not always to magnify things, but also to reduce the size as well. So we will use models for the atoms. Chemistry is of course an experimental science which requires lab practice, but there are also lots of theoretical concepts that have to be supported with models. Models come in different sizes and shapes, and their price will also vary. Some are easier to deal with, others are less sophisticated. Why don't you show? Why don't you see them? Why are some black? You have black balls and sticks attached to them, of course.
The black balls represent carbon, and they are black to show its color, to simply show its color, which is carbon black.
And why do we have 4 sticks attached to the ball?
Because Carbon has a valence electron of 4. So to show the valence electrons, we have 4 sticks attached to it.
Is it true that the number of valence electrons is equal to the valency of the element?
No.
Then what is it? What's valency? Does it have anything to do with valence electrons?
The valence electrons are the electrons that are found in the outermost shell, and while the valency is the amount of electrons needed to make that element stable.
Okay. Well, chemistry is easier when we use elements from period 2. Which elements are in period 2?
Lithium,
Mm-hmm.
boron, carbon.
No, there comes another element between boron and lithium.
Yes.
Lithium from the alkaline earth.
Magnesium.
That's one. Period 2. Yes, beryllium, lithium.
Lithium, beryllium, boron, carbon, oxygen, nitrogen,
Mm-hmm.
oxygen. Then comes neon.
Yes. Okay.
There is fluorine between nitrogen and.
I think she said fluorine.
She did.
Oh, you skipped it? So why don't you do it again? Say.
Lithium, beryllium, boron, carbon, nitrogen,
Oxygen.
or fluorine, and neon.
Okay. These are period 2 elements. Why are they called period 2 elements? Read it. Liu?
I think because the valence electrons are in the valence shell of the period.
Okay. In the ground state, they use only 2 shells. In these 2 shells, there are how many orbitals? In the first shell, we have only 1 orbital. In the second shell,
3.
the second shell. What is this general formula? 2n squared. What does n stand for?
The quantum principal number.
Okay, principal quantum number, which represents the number of the main energy level. So if we are talking about the second main energy level represented by 2, then what's n squared? 2 squared is 4. That is the number of orbitals. Why do we multiply that by 2? 2 times n squared. N squared is the total number of orbitals in the n shell. Why do we multiply that by 2?
To get a number of electrons.
Because in one orbital,
The maximum number of electrons is 2.
So the 2n squared represents the maximum. Can a main energy level have less than the maximum? Is it possible?
Yes.
Yes. For carbon, which is a member of the second period, the maximum allowed in the valence shell. What is the valence shell, Maharat?
The last shell on
The outermost shell. That's the shell with electrons in it. Is the second one. So how many can it accommodate? 4.
Actually, the
N
maximum
squared.
number is 8.
N squared. N is second, so 2 squared is 4. But you multiply that by 2 because in each orbital you can put 2 electrons at most. So maximum it will be 8. Carbon is one of them. So how many electrons can it have maximum?
8.
8. But does it have 8?
No.
How many does it have?
4.
4. But don't forget that The atomic number of carbon is 6. What is the difference? 6 minus 4 is 2. What is that 2? Where are they? Where are those 2 electrons?
It's in the inner shell.
In the inner shell. They are buried. They don't participate in
Reactions.
the chemical reaction. So they are not important to us. Maybe they are of importance to physics, I don't know. But for chemistry, no. So we have 4 valence electrons in carbon. How many electrons should it acquire during a chemical reaction to fulfill its desire to have the octet? 4. That is what we call the valency. So if we assume it is reacting with hydrogens, then each hydrogen is going to contribute how many electrons? 1. So the maximum number of hydrogens that will combine with carbon will be 4. That is its valency. Okay, in front of us we have various models of atoms. They come in different shapes, different colors, like the black representing carbon. We all know carbon is black. Oxygen, we don't see it, but it's involved in combustion where heat is generated. So because it burns us, we've given it red color. The others are just conventions. The white for hydrogen, you see numerous balls. This plastic flexible tubings are for bonding, for connecting an atom to another atom. The blue is for nitrogen. The green is for halogens. It could be chlorine, fluorine, bromine, but sometimes we have with one stick attached to it, which would make it part of the halogens. Lydia, you see, we say this is carbon. Why does it have 4 sticks attached to it?
The sticks are used to describe the valence electrons, and since we have carbon has valence electrons 4, and the valence electrons are the electrons that are found in the outermost shell, so it's used to describe the valence electrons.
Okay, as a follow-up, this is blue, it represents nitrogen. How many valence electrons does nitrogen have?
5.
So then why don't we see 5 sticks?
These ones are used to describe the amount of electrons that are used to make the nitrogen element stable, and since it needs 3 valency, it has a valency of 3, so it's used to describe the amount of valence electrons that are needed to make it stable.
So would you like to revise what you said earlier about carbon?
Well, now since carbon has valence electrons 4, it needs 4 electrons to make it stable, so these are used to describe.
So the valency, is it the number of valence electrons or the number of electrons it needs to complete its outer shell?
Valency is the number of electrons that are needed to complete this.
So because carbon has 4 and octet is 8, 8 minus 4 is 4. So its valency is 4. For nitrogen,
It has
how many valence electrons?
5.
5. To have 8, it needs 3. So the 3 sticks represent the valency of nitrogen. How about the white ball?
Like this one, it's used to describe hydrogen, and it needs only 1 electron to be stable. So this is the valency of hydrogen.
Oh, were we not talking about octet, 8?
Yes.
All of a sudden now you say only 1 is needed? Is 1 plus 1 8?
No, it's not.
Then how is that?
That's
Okay.
for hydrogen to be stable, only 2 electrons are needed.
Okay.
That's right. It's a debate.
Which period does hydrogen belong to?
First,
Okay. The first period elements need only 2. So their so-called octet is duet. So 2 minus 1 is 1. So because it had 1 valence electron, it requires
Only
an
one.
additional 1. So that stick is representing the valency. Okay. Thank you very much. Now, Fikr, can you make ammonia?
Yes.
I already made it.
Yes.
No kidding. Make your own. By the way, you can make your own models at home, especially you girls like to. You like candies?
Yes.
What else? Do you always eat candies or yes, Liam? What do you chew? Chewing gum. Do you think it has any role for making your own models?
You can use the candy as the atoms and use chewing gum as the sticky bombs.
No, candies are expensive. Don't waste them. Once the chewing gum is done, roll it in a paper so that it doesn't become sticky to you. Then you can use toothpicks to represent the bombs. So you can form such kind of model. I know it's not going to be perfect in terms of angle or bond length, but who cares? As long as you understand what you're trying to build. So don't waste your use gum. Yeah, you save them, wrap them with paper, and then use toothpicks can represent that. Okay, so you made ammonia. What is this angle? 9.5. Mehrat, can you make water?
Actually,
You dismantle them and give it to her. Okay. What atoms do you have?
Oxygen and 2 hydrogen.
Can you speak louder?
Oxygen, we have an oxygen atom and 2 hydrogen.
I have a hearing deficiency, so you guys.
We have 2 hydrogen
okay.
molecules and 1 hydrogen atom.
1 atom of oxygen and 2 atoms of hydrogen make 1 molecule of water. Who can make a molecule of hydrogen? Ready it? Molecule of hydrogen. Wouldn't one be enough?
a molecule of hydrogen contains 2 hydrogen atoms.
So a molecule is made up of,
2 atoms of the
is it
same
always 2 atoms?
No,
2
or more.
2 or more. How about sodium? It's monoatomic. So it can be considered as a molecule. It is stand alone. A molecule is something that stands on its own. So the group 1 metals, well, unless you vaporize, you will not get separate atoms. But theoretically speaking, Na, it can be taken as a molecule because it stands on its own. But H doesn't. Okay, H2. Who can make carbon dioxide? Okay. So you take carbon.
And
I'll take 1 atom of carbon.
Okay.
Then I'll take 2 atoms of oxygen. But they haven't fulfilled their valency. So I'll need to make a double bond because this is all the atoms that I have. So this is carbon dioxide.
It is a linear molecule.
Yes, it is.
What do you mean it's linear? How many atoms does this molecule have?
It has 3 atoms.
3. And do you make a straight line?
When we draw it.
Yeah, when you connect them.
Yeah.
So there is a straight line connecting all 3. Is this bond polar? The carbon-oxygen bond polar or non-polar? Non-polar.
The carbon to oxygen.
Yeah,
I think
the
it's
carbon to
polar.
oxygen.
The one on.
Yeah, guess this one. Is this polar or non-polar?
The polar.
Are the electrons shared uniformly? Do they have the same desire for electrons?
No.
Is oxygen as electronegative as carbon? No. They have different electronegativity. So electrons would spend most of their time around carbon or around oxygen. So this area would be more negative, making this less negative. So that's poles, positive and the negative poles. So this is polar. How about this one?
It's also polar.
Same thing. But to explain polarity, we use dipole moment. What's dipole moment? Can you define dipole moment?
Dipole moment. It means there's a partial negativity and partial positivity.
But how do we measure dipole moment? There is a unit. What is the unit for dipole moment? Maybe you never heard of that. Debye. Peter Debye. I don't know where he was from. I'm sure he was not from Adigrat. He's from Europe. Was the person responsible for establishing this. So he's credited. His name is attached with the unit for dipole moment. And it is the magnitude of the charge. It can be this one or this one, the same magnitude, but they have different sign. The absolute value is the same. So the charge times the bond length is what we call the dipole moment. How about for this? The same thing. They have opposite. Dipole moments are vector quantities. They start from the positive and point towards the negative. So this is pointing in this direction, this is pointing in that direction. They have the same magnitude, so they cancel out. So what is the dipole moment of the molecule as a whole? Zero. So it is non-polar. Please put this in water. Does it dissolve?
No.
Like? Dissolves?
Like.
So are they like?
No.
From practice, does carbon dioxide dissolve in water?
No.
Well, you can't force it to dissolve. You know, amboha, it is carbonated. There is carbon dioxide in it. But if you open the gate, the prison gate, what happens? They escape, they run. But under pressure, and when it is capped, they stay there. But if you open the lid, they escape. So they don't dissolve. The same thing is true for oxygen. Is oxygen polar? O2? Why not? You have, can I get one of your red balls? Thank you. Maybe does this fit in here? No, it doesn't. So the double bond, I think we made carbon dioxide.
Yes.
Not this one, no, using this board. Yes, thank you. Another one. Another one. It's enough. This is O2. Okay? Show it to your friends. It is polar.
No.
Yes, it is. Oxygen is the second most electronegative element. How dare you say it is non-polar when it is very electronegative? Right?
Because it's a molecule, and when we say oxygen is the second most electronegative element, we're referring to the one oxygen atom, not the two together. And when two oxygen atoms interact, it creates the same kind of electronegativity. So there's no difference between the two. So it's non-polar.
Well, this is 3.5 or 3.6 on Linus Pauling's electronegativity scale. The same thing for this. This minus this, 3.5 minus 3.5 is 0. So where would the electrons be?
In the middle.
In the middle. So would you say this is negative and that positive?
No.
No. So it is non-polar. So would it dissolve in water?
No.
No. Especially if you warm it up, all gases like carbon dioxide, which is non-polar, and oxygen evaporate. How about ammonia? Oh, this is ammonia, right?
Yes.
Is it polar or non-polar?
Polar.
I think it's polar.
Why?
Because there is a difference in the electronegativity of nitrogen and hydrogen. So this means that there is also a difference in the capacity of sharing electrons. So that makes it polar.
I think we will have to discuss this a bit further. Can I take the molecule? Thank you. She rightly said there is difference in electronegativity. If I correct it, if I remember this correctly, Linus Pauling has assigned nitrogen electronegativity of 3. For hydrogen, 2.1. 3 minus 2.1 is 0.9. That is big enough to make this one polar. The electrons would like to be around nitrogen than hydrogen. I can give you a personal experience. If I take my kids to be electrons, they spend most of the time around me, not around their mother, because she's a bit repulsive. I'm a very warm person. So nitrogen is like me. So this bond is polar. You can measure its polarity by the dipole moment. The bond length is measurable, and the charge difference would give us the dipole moment. So it is directed inwards. The same thing is true for this one. The same thing is true for this one. There is one thing that we're not seeing here. What is that?
The lone pair.
Lone pair of it. Thank you very much. Lonely. It's a loner. Why don't I call this a lone pair? Why don't I call this a lone pair? Why don't I call this a lone pair?
Because we're hydrogen.
They are being shared between nitrogen and hydrogen. How about this lone pair?
It's not being shared.
It's entirely possessed by nitrogen. So around here we have electron density in this way. So if you add all this and then up, it would be what? The sum would be, no, it doesn't cancel out. It doesn't cancel out. do we have? No, actually not. Say, if this was, if we had 3 holes that would make this planar, like this. If we had 3 holes that would make it planar, the bond angle would be 120. Then all 3 would cancel out, making the whole molecule non-polar. But it is not planar in this case. The angle is 109.5. So all point coming from down, slightly pointing up, up, up. And there is another electron density up. So the sum of these vector quantities is real positive. So ammonia is polar. Would you think it dissolves in water?
Yes.
Yes.
Yes, it does. How do we make ammonium hydroxide?
By dissolving ammonia in water.
Yes, you dissolve the gas ammonia in water. This is what? Basic or acidic?
Basic.
What makes it basic? What is the Arrhenius definition for acids and bases?
They give off a high.
Okay, I know you know this. What is the Lewis definition for acids and bases? The definition depends on availability of electron pair. Don't we have an electron pair here? 3 to be donated. From the water, H plus comes, attacks itself here. The water can be considered as base or acid when it reacts with ammonia.
As an
acid.
As an acid, it's a proton donor. This is a Lewis base because it is electron pair donor. So now we have this, like this. NH4 plus ammonium. And from water, what do we have? What is left? OH minus. The 2 are ions, so they dissolve in water. Ammonium hydroxide is ammonia plus water. Ammonium hydroxide. So if you open the bottle of ammonium hydroxide and leave home, when you come back, you won't stand the smell. Why? What is in the air? Ammonia. The ammonia is released, and eventually your ammonium hydroxide gets weaker because the solute has the solute has left. So, and left open bottle of ammonium hydroxide is no longer ammonium hydroxide. It's just mere name. Otherwise, the ammonia has left. So you have only water, or it is at most a very weak ammonium hydroxide solution. So, is this clear how we build molecules to see the molecules that we otherwise don't see?
Yes.
Models are helpful, but models are models. They don't really replace the molecules. If you want them to react, will they react?
No.
No, they don't. So there is a limitation. But is the world better off with them or in their absence?
With them.
Yeah. So we need to be helped with models. Okay, so why don't you make carbon dioxide? You already have one. Plus water. Can you make a molecule of water? Okay. Now, if these two react, how do they react? Of course, glucose has how many carbons?
6.
So how many carbon dioxide is the minimum requirement? Minimum 6 carbon dioxides, because They are the only source of carbon. We don't get carbon from any other source. So if you are going to make glucose, which has 6 carbons, then you should start with 6 carbons. If you want, you can make 6 of this, but in the interest of time, let's not do that. But so 6 carbon dioxides. In glucose, in addition to 6 carbons, we have what?
12 hydrogens.
12 hydrogens. Where do the hydrogens come from? From carbon dioxide?
No.
No.
From water.
Who is the sole provider of hydrogen?
Water.
So can we make glucose in the absence of water?
No.
These days, what is in short supply? Now we're talking about drought. We didn't get enough rain in the summer, so we will not produce enough food to feed ourselves. What was the shortage? Was it carbon dioxide?
No.
In fact, these days, carbon dioxide is plenty. Where does carbon dioxide come from? Burning, yes. When we cook, what else?
Respiration.
Respiration. What else?
Deforestation.
Yeah, it's going to burn.
Decomposition of dead
Plants, animals. Okay, what else? You're forgetting one important industry.
Factories.
One industry. Mughal is famous for cement. Cement is made from calcium carbonate. The calcium carbonate is decomposed into calcium oxide by releasing carbon dioxide. So when you see huge cement factories, you should be happy because you are getting cement, but you should also be worried that you are producing as much carbon dioxide. I advise the government to tell these people to do what? To suck their carbon dioxide. They should not pollute the environment. So what should they do?
Plant trees.
Plant trees. The trees will take this carbon dioxide, reduce it with
Water.
hydrogen from water to glucose. So if a single molecule of glucose is going to have 12 hydrogens, what is the smallest number of water molecules you need?
6.
Because each one comes with 2. So 6 carbon dioxide, so that we get 6 carbons for glucose, and 6 water because we need 12 hydrogens. So 6 carbon dioxide plus 6 water gives us a single molecule of glucose. We've talked about the carbon, we've talked about the hydrogen. What else is in glucose?
Oxygen.
How many atoms of oxygen? 6. So who provides us with oxygen? Carbon dioxide, it has oxygen, water has oxygen. Let's not worry who does this, but there is enough of that. In fact, more than what we need. The 6 will come with 6, the 6 will come 12. We have a total of 18. But we need how many oxygens in glucose?
6.
So what shall we do with the rest, the balance? Which is? How many would be not needed for glucose? 12. So they should be removed in the form of oxygen. But oxygen is diatomic. So how many molecules?
6.
So what is the balanced equation? 6 carbon dioxide plus 6 water gives us 1 mole of glucose.
And 6 oxygen.
So does this show mass is conserved?
Yes.
No. 6 plus 6 is 12. There 1 plus 6 is 7. You are changing 6 and 6 molecules, 12, into 1 glucose and 6 molecules of oxygen, a total of 7. 12 into 7. Is there no decrease in number of molecules?
I don't think so.
Because since we said the glucose contains 6 carbon, 12 hydrogen and 6 oxygen, the same amount of carbon, hydrogen and oxygen are found in the reactant state. So,
Liu, what do you say?
In my opinion, when we react carbon dioxide with water, we said it gives glucose and oxygen. The carbon and hydrogen and oxygen before the reactant are equal after the product. That means when we balance them, they give equal amount, so the mass is conserved.
In addition,
Yes.
I think the amount of product is higher than the one we used to form the product, the carbon dioxide and the water.
So this is not following the law of conservation of mass.
In order to obey the law of conservation of mass, we need to balance them.
Yeah, but we took 6, we got 1 and 6. 12 being converted to 7. It is in line with the law of conservation of mass.
Yes.
Really?
Yes.
Okay. You explain.
Because when we are conserving, in the law of conservation of mass, we're conserving the number of atoms, not the moles. We are the number of moles. We have first 6 moles, the molecules, so the moles of the carbon dioxide are 6. But we still have 6 atoms of carbon and 12 atoms of oxygen. So when we go to the product side, we still, although we have 1 mole of the glucose, we still have 6 atoms of carbon within it. And we still have 12 atoms of oxygen. So we are conserving it, not the number of moles, but the number of atoms.
Can you state the law again, please?
The mass of the reactants should be equal to the mass of the product.
I will give myself, for the sake of chemistry, chop me into 10 pieces. Will you? Don't lose even a single drop of blood or hair. You conserve everything. You know, now I am 92 kilograms. What will I weigh? Not me, the body, a dead person. How much will my body weigh after I die? 92. I was 1, now you have made me 10 pieces. We're not talking about conserving the number of molecules. It is the mass. The mass is the same. So don't confuse the mass with the number of molecules or moles. So Radiate has stated it clearly. Thank you very much. So I think today's lesson has been successful. But before we finish, this looks beautiful, right? Can I put it on my head? Maybe it's dusty. Who cares? If it will make you happy, I will do it. This is a representation of benzene. Have you ever used benzene, or has anybody in your family used benzene? I don't know. Is it an important commodity for you guys at all?
Yes.
Yes. So you're familiar with this molecule?
Yes.
Okay. What do you do with it?
We use it for cars.
In cars. Yes? You have that experience? No. This is a very important mistake. I'm glad that you made a mistake.
Can I explain?
Yes.
I think the one we use for our cars and this one is not the same. The one we use for our cars is a combination of hydrocarbon gas.
It's a mixture.
Yes. And this one is aromatic hydrocarbon itself.
The aromaticity compounds like benzene itself and its derivatives. We use such molecules extensively in making drugs to fight diseases. But that benzene with an I, this is B-E-N-E-Z-E-N-E. Did I say it right? Doesn't matter. But the one with I You can read it as benzene if you like. I think we borrowed it from Italians. Is a mixture of alkanes. It's a fuel. This is cancer-causing molecule. We have to be very careful. C6H6 is a different molecule. I carry this around with me every time I go to my lecture. I just show it to them. So we'll stop it here. Thank you for your attention.
Thank you.